Hi, everybody. My name is Yisrael Mirsky. I'm a PhD student at Ben Gurion University. I'm also a project manager at the Cybersecurity Research Center there in the university. I manage a project for the Israeli Ministry of Science. Today, the primary author of the content of this talk was not able to make it because due to the birth of a daughter. So as a co-author, I'll be filling in for him. The talk I'd like to speak to you about today is about bridging air-gapped networks. And I'd like to go over different methods of bridging air-gapped networks. And most of the methods that I will show you today were developed in our cybersecurity labs and published in order to bring awareness to this issue. So, what is an air-gapped network? So the typical approach to securing a network is that we put some sort of firewall between our corporation or sensitive network and the rest of the internet. And the air-gap approach is a security measure where the approach is that if we have some sort of physical disconnect between our network and the rest of the world, then our network is pretty much secure. There is no way for the attacker to transmit information into the network and transmit information out of the network. So this is basically what the attack model really looks like. You have the attacker somewhere in the internet per se, you have an air gap, and you have the air gap network. Some examples of networks that may be air gapped, you have, let's say, military defense systems, financial systems such as the stock exchange, industrial control, SCADA, critical infrastructure, power plants, refineries, traffic control, and the list goes on. But as we know that the approach of air-gapping a network is not a foolproof approach, and we've seen many different malwares which have infected these air-gapped networks. So what's the adversarial attack model for infecting an air-gapped network? So first, there usually is some sort of initial infection. Either a malicious or deceived insider plugs in some sort of infected media, a USB, or plugs in his phone to charge, whatever it may be. Or there's some sort of attack on the supply chain where the chips or motherboards go into the air-gapped network before they even reach the network are infected with some sort of malware. So we know that it's possible to do some sort of, for the attacker to infect a air-gapped network. And the real question is, what does he do afterwards? So some examples of the actions that a malware within an air-gapped network might do is steal sensitive data, manipulate the control systems, delete records, deactivate some sort of security measure, DDoS, self-destruct, either cause a lot of havoc or just erase its own tracks. So once we know that the attacker can get some sort of presence within an air-gapped network, the question is how can he send commands to the infected computers and receive information afterwards? And the reasons why we would want, or the attacker would want, some sort of inbound or outbound channels is as follows. For inbound channels into the air-gapped network, the attacker could send commands which gives some flexibility on the attack, or most importantly, when to perpetrate some sort of DDoS if needed. Update malware, sending new modules, fixes, or changing encryption keys, and so on. For outbound channels, you could possibly receive passwords or exfiltrate whole documents. And most importantly to him is reports on the progress of the infiltration, where the malware has gone, what assets it has access to, and so on. So that brings us all the way to the main subject of what I'd like to speak to you today, is the three different ways of bridging the air gap. We have thermal channels, radio channels, and acoustic channels. The thermal channels and radio channels were developed in our labs and published to bring awareness. And the acoustic channels, if we have time, I'll get to that, are as a previous subject published by other researchers, which I will cover briefly. So let's start with thermal channels. The first idea is what we call HVACR. So we know that modern PCs have thermal sensors inside them to determine what temperature the CPU is, the case is, and so on and so forth. And these sensors can be used to determine the environmental temperature around the computer. So really what we're thinking of here is, well, if we can change the temperature around the computer, then we can effectively, by raising and lowering the temperature, we can send information to these computers. So the big question is, well, how do we change the temperature around the computer? So one way to do this is to hack the HVAC system. The HVAC system is the heating, ventilation, air conditioning system found in most large buildings. It is a centralized system to handle all the lighting, power, and most importantly, heating and cooling of the building. So just doing a quick search using the Shodan.io search engine, we looked for an example HVAC system called the Tritium Niagara AX platform, and we found about 36,000 different web portals completely exposed, with about 269 which are protected by HTTPS. And a lot of these web portals are to these HVAC systems to large corporations and industries. So just goes to show that these HVAC systems have vulnerabilities, and this main connection that the attacker can get to this to the HVAC system is through these web portals, which are used by the personnel to manage the HVAC system remotely. So just, it sounds kind of James Bondsy, but here's an example from an article in 2013 where researchers hacked a building control system at Google in the Australia office. And just by they just found the portal, they did a very simple password attack, and they got access to the HVAC system, which gave them floor plans, it gave them access to change the temperature in the different rooms, which is, of course, most interesting to us. So here again, here's the attack model. We have the attacker somewhere in the internet, has access to the air conditioning system, and is able to manipulate the temperature in the entire building, kind of like a broadcast system to any possible infected computers there to send them information. So this is clearly an inbound channel. And as we mentioned before, inbound channel is interesting to the attacker because he can cause an attack to happen when he wants it to, or he can possibly change different properties within the malware, give send updates. So how do we do this? Very basic protocol to send information. The air conditioner in the room will, let's say, lower the temperature, send to 0, raise the temperature, send to 1. And the receiver, also again, a very simple demodulating protocol. If the current trend of the temperature in the room is going up, then it assumes it's a 1. If it's going down, it's a 0. And if it's more or less staying the same within some sort of threshold, then it assumes it's the same as the previous bit received. And we put this all into a framing process where the transmitter, in order to send information to any listeners, we first put a preamble so that the listeners can determine whether this is a mistake or perhaps some sort of noise. And also, of course, to synchronize on the bit sequence. An opcode. Opcode could be, I want to perform the attack now, delete a certain file, a parity bit just for a bit of integrity check, and a payload if necessary. A quick overview of the high-level protocol. So at first, we'll assume that the attacker will only do this kind of attack during the evening, where there's fewer personnel around to notice the changes in temperature. Generally, we found only just about a few degrees difference is enough to send the signal over. If during the evening the malware receives a preamble, it will then investigate the frame integrity by checking the parity bit and also correlating the opcode to the payload, if it makes sense. If that passes, then it would collaborate with peers, other malwares in the network, which it has access to, and they could, by majority vote, kind of determine, well, I got this and it sounds correct, well, let's compare notes and see if we all got the same message. And of course, if they all get the same message, accept the frame and perpetrate the action. And of course, there's also some sort of process of self-destruct. If the malware hasn't received the command in a very long time, it will just erase its tracks. Perhaps it got moved to a location. It's too far from the air conditioner. It can't receive any signals. It's just kind of a backup. So again, these are all just things I'm just pointing out here, so just to keep an eye of an idea of that it's possible and the kind of things to look for. In experimental results, we got about 40 bits per hour in a very small office scenario. We didn't fully test in all sorts of different scenarios, all different kinds of HVAC systems. It was a very simple test to show the feasibility. The main question I think we can ask here is, what about the internal interference? When somebody starts using the computer, the CPU starts getting hotter, and it could affect the thermal sensors within the motherboard. So we just a quick analysis. We did different kinds of actions on the computer: video playing, web browsing, and word processing. At the bottom there, you see the CPU usage. The yellow line there is the CPU thermal measurements, and the gray line is the thermal sensor located on the motherboard. And as we can see there, that's the best sensor to really look at and to get an idea of what the environment is sensing, and it's hardly affected by the whatever the computer is doing, unless of course you're doing really intensive work there. But the common idea is that we're looking at the common desktop that's close to some sort of asset. So countermeasures for HVACer, we could disable or better secure these web portals to the HVAC system, monitor environmental temperature changes, and malware signatures, anything like possibly looking at these kind of thermal sensors that may seem suspicious. So let's move over to the next type of thermal way of bridging the air gap, and we call this one bit whisper. So we know that computers can receive thermal signals, but we also know they can emit heat as well. So this is a very useful property, since we can now not only have a computer send signals, but also receive. And then if you happen to have two computers next to each other, we can make a bidirectional half-duplex channel, sending information into the network and receiving information from the network. And what kind of cases would this be? Well, many times you have leased computing spaces where a lot of different machines are kind of piled on top of each other, belonging to different corporations, and these can be used to bridge the air gap. And we also found that it can be achieved within virtual machines. So here again, a quick view of the attack model. And looking a bit closer, when we performing our tests, we found, of course, the amount of heat that comes out of putting a large load on the CPU or the GPU. It's not quite as hot, of course, when it reaches the other computer, but it's enough. We're using different smoothing techniques or moving average filters, very basic ways of getting rid of the noise. We were able to pick up these signals. Here's just a few different setups that we used in our experiments. Okay. And just a note on the side of here, different kinds of protocols that we tested. So we tried the differential non-return to zero, very similar to the first protocol I mentioned with HVACer. We impede a very large load on the CPU to send a 1, and we do nothing to send a 0. And time index signaling, which is where we take a time frame and we split it up into 16, for example, 16 slots to represent the hexadecimal or whatever it may be, and we send a ping at the right time to kind of indicate the value that we want to send. We repeat that over and over again. So in terms of results, the time index signaling, we got about 7.5 bits per hour. It's pretty slow. But again, if you have like a long-term situation, two computers sitting next to each other for a very long time, it's feasible to consider sending small pieces of information to one another, whether it be passwords or maybe commands to start an attack and so on. So bit whisper countermeasures, we could enforce better zoning policies when it comes to air-gap networks, not have air-gap network machines near any computer machine that may be connected to the public network. Perhaps strengthen the air conditioning to weaken the signal between the two, malware signatures, and again, environmental sensing. A quick demo. So we have the computer on the left is supposedly connected to the internet. The computer on the right is connected to the air-gap network, not connected to anything. And I don't know if you can see so well, but there's a thermal camera next to in the bottom corner. And we're basically sending bits of information to tell it, to perpetrate an attack now. The malware receives it and perpetrates the attack with that little toy you see on the corner that fires the missiles. So this video is actually being played about 16 times speed. So just the idea, it's not super fast, but again, it's enough to send information. Okay, so let's move over to the second type of way of bridging the air gap, and that's radio channels. Of course, a bit more, I'd say, likely to be used and more dangerous. First, we'll start with AirHopper. So many workplaces have this policy of bring your own device, which means that a large corporation won't supply you with a smartphone and consider it secure. They'll say, bring your own smartphone to work. And of course, that brings a lot of concerns. But in our case, we know that smartphones can be used to detect and receive all sorts of different kinds of radio signals. And if we can get computers to emit radio signals, then we have a fantastic way of sending information from computers to any nearby smartphone. So the attack model looks like this. Some user comes within range of a computer emitting a signal, and in our case, on FM radio modulations. Since every single smartphone, or almost every single smartphone, has an FM chipset inside, you can receive and demodulate FM signals, we're able to receive FM modulated signals and, of course, pass along to the attacker. So the big question is, how do we turn a computer into an FM broadcasting system? So just a quick aside about how antennas work. So antennas emit radio waves by oscillating current through their terminals. And radio waves are characterized by their frequency, how fast the oscillations are, and the amplitude, how large the oscillations are. So based on previous works, we didn't find this idea, but based on previous works, that it's possible to send to the monitor different kinds of images, and due to the size and the shape and the refresh rate of the images, we're able to use the display cable, not quite the cable that's being shown here, but the display cable to emit radio waves. And in the AirHopper that we published, we found a way of specifically emitting it on FM channels, and of course using a regular smartphone to pick up those signals and pass along the information. The way we do that, because again, FM is an analog type of modulation, so to send a type of set of bits, we'll send a tone over that channel, higher tones, more values, and it's just really just a mapping between tones. And the PC, when it has some text or information it wants to send, it looks up the binary it needs to send, the mapping to the tone, and then of course that causes the display to show the right image in the corner or in a very small location, and cause the radio signals to be emitted from the cable. And the reverse process, of course, from the smartphone. The smartphone looks at the right broadcasting channel and demodulates it accordingly. So in our experimental results, we found that, of course, some smartphones have built-in antennas, some don't, and the ones that don't, if you plug in the headphones, it acts as an antenna. So without an antenna, you get about most 1 meter range. With an antenna plugged into the phone, you can get up to between 8 to 20 meters range. So that means somebody can come to work, put their phone on the table, perhaps they know or don't know that their phone is infected, and be receiving information from a computer nearby or possibly in a different room. In terms of data rates, not crazy fast, but much better than the thermal channels. We can send about 1 kilobyte in about a minute and half a megabyte in about 11 hours. So again, it depends on the kind of information you're interested in exfiltrating from the air-gapped network. But again, a process of day in, day out, bring this phone in, if it's a lot of information, or if it's just simple key logging, it's very feasible. Countermeasures, so again, strict zoning. We can do perhaps insulation better on the cables. The display cables, we cover them with some sort of resistant material, will probably mitigate this problem altogether. Jamming, we could perhaps emit some sort of noise on the right frequency bands, and again, signatures, look for some sort of strange behaviors that have to do with graphics-related manipulations. Let's take a look at another demo. So the computer on the side there has the malware running, and this phone right next to it is not connected to the internet. Both devices are connected to the internet in this case. And the device also has some sort of listening malware. Listening malware. And we're going to use it now to receive messages from the keylogger that's on the computer to the right. So as you see, he types in a message top secret and it starts appearing immediately on the smartphone right next to it. I don't know if you saw, but the small little peaks were, of course, the tones that were being sent were corresponding to the characters. And just to demonstrate that it could be received from other rooms, here's another smartphone that was just down the hallway, received the exact same message. Okay, so let's move on to the last radio type method that we developed in our labs to bridge the air gap, called GSMEM, which we published not too long ago. Okay, so feature phones are phones that don't have Wi-Fi or Bluetooth or any extra capabilities like those old Nokias that we had like a couple of years back. And these feature phones are allowed to be brought into restricted zones. They're still in the policy. I don't know if it changed since we published this work, but it still was, a few months ago at least, still in the policies of these large corporations to be people who are entering restricted zones are allowed to bring feature phones. They're not allowed to bring smartphones, but allowed to bring feature phones. And feature phones still have within them, of course, the chipset in order to receive GSM or other technology signals. And what we found is that we can exploit the CPU memory bus of any standard computer to emit radio waves exactly on the bands of cellular phones. And we'll get to that in just a moment. So here's the attack model. Again, anybody brings in a feature phone or even a smartphone within range of a computer who's broadcasting on the signal can receive exfiltrated information and pass it along to the attacker. So let's talk about how the transmitter works. So our first observation was that when we cause a large transfer between the CPU and memory, there's a buildup of oscillating current on the configuration. As we talked about antennas, the oscillations release radio waves, and the observation 2 basically showed us that, well, the clock speed of the motherboard determines the oscillations, and that just happened to be around 800 megahertz, which quite fortunately was, to our surprise, on the bands of cellular technologies. So what you see at the bottom is a plot. The blue line shows the regular noise floor, could possibly be other cellular phones communicating or other computers in the room causing noise. And the red line shows the added energy that is received across the spectrum when we cause this large transfer between the CPU and the memory. And it's important to point out here, it's not just any transfer. You have to actually bypass the cache in order to get this large buildup to occur, and then the emission will happen. So we affect not just the GSM, as the title GSMEM may imply, though we tested specifically GSM. But as we can see here that all these different bands of all the different technologies receive the signal quite well. So how do we send a bit? So to send a 0, we do nothing for t seconds, and to send a 1, we cause a large transfer for t seconds. And once again, we put this in a frame every several bits. Every 12 bits, we put a preamble in front of it for a few reasons. One, synchronization. Again, because we're talking about wireless communication, the receiver can move away from the transmitter, so we have to adjust thresholds and so on. And some interesting properties about the transmitter, the malware that's on the computer. First of all, it only has a 4 kilobyte memory footprint. No root or admin privileges are required for this to happen, and no APIs are used, so which is a bit trickier to catch it. Also, we note that we tested it on Intel AMD architectures. We assumed it also affects other architectures as well, and it works on Windows as well as Linux. So receiving the signal, well, now for a phone to get from the phone to get access to the raw signals, you would actually have to modify the firmware of the baseband chipset. And although it's kind of out of the capabilities of the average person, because you basically need access to closed source code, we've seen this doesn't really deter highly motivated threats, so we assume this is still considered a threat. But in order to prove our point, we used an old feature phone the Motorola C123, and use an open source baseband software, Osmocom PB. In order to show the quality of the possibilities of receiving these transmissions, we also used a software-defined radio kit here, as shown in the bottom corner, to see how really far the signal reaches. And receiving, the receiver will just look at the best frequency, the one with the least oscillations, look for the payload, the preamble. Once it sees the preamble, will extract the payload. So experimental results. So with the old 9-year-old phone, we got about 1 meter's distance in terms of range. So somebody comes and puts their phone, or in this case, someone enters a restricted area with 1 meter range with this old feature phone. Of course, if the feature phone were, it were a little more capable or had the capabilities of the USRP, we were able to get far better distances. As we see with the USRP, we're able to pick up the signal about 40 meters away and even further. And a few other interesting things we noticed is that more channels, more memory channels, increased the output of the channel, of this signal. And orientation of the case with respect to the receiver has an effect, but it's not too detrimental on the signal quality. In terms of data rates, so with the old phone, we were able to get within a few minutes send some quite interesting data. And with the USRP, we're able to get within a few seconds quite a bit of data. We can send almost anything. Countermeasures, interference, shielding, and again, stricter zoning, better policies, and bringing devices into air-gapped networks. Quick demo here. So here we have a computer, presumably air-gapped, and we have the old Motorola C123 phone with no connectivity in it. And it's just sitting there sniffing, looking at the GSM band and trying to look for our signals. The keylogger on this computer over here, receives the signals and causes the transfers across the CPU memory bus. In order to send signals to the Motorola phone. And it's a little hard to see on the screen here, but the same thing that was typed on the computer is now appearing on the Motorola screen. Okay, so that's it for radio channels. Now, just for the sake of completeness, I will mention also acoustic channels. This method was a most centric work that was published by Michael Hansbach and Michael Goetz. And the general idea is that, we can transmit information through a speaker. We'll use ultrasonic signals. Ultrasonic meaning it can't be heard by the human ear. And the receiver will be any microphone in the area, whether a part of a laptop or a smartphone. This has also been rumored as the way that, if anybody heard of bad BIOS, the way information has been hopping between different infected computers there. So the attack model is basically a mesh network where all sorts of devices infected with this malware speak to one another through ultrasonic communications. And they all make hops to one another in order to pass along information until one happens to be connected to the internet and then passes along quite easily to the attacker. And this, of course, is an outbound channel as well as an inbound channel. Countermeasures, we could perhaps in these very sensitive areas emit ultrasonic noise. It wouldn't affect anybody but perhaps dogs. And we can also try and do better strict zoning policies, but with a malware like this, it's very tricky. You don't know who exactly has been affected, who's passing along information. Someone passes along, picks up a signal. It's a very sticky situation. Okay, so in conclusion, we reviewed 3 types of channels that can bridge air gaps. And I remind you again, with the assumption here is that the air gap network has already been infected by some sort of insider or infected media or supply chain attack. And the takeaways are, I guess, are air gapping does not provide a guaranteed disconnect. And that awareness of these different kinds of bridges through these different kinds of channels can help us harden these air gap networks. And that's it. Thank you very much.
Test.
Nimmst du das? With the method of transmitting data via the display cable,
Yes.
is there any disturbance visual to the user?
To the user. So that's actually the only paper here that, aside from, of course, the acoustic channels, that I was not directly involved with. I do believe that they were able to do it in a way that the user did not notice. I would suggest, if anybody's interested in looking deeper into how they did it, what kind of images and the way to do it, you can take a look at the paper that was published there. But I do believe that they accomplished this without too much interference. And even if there was interference or to the user, he noticed some sort of strange, thing going on there. This could also be done, perhaps, when the screen is off and nobody's looking at the screen and so on. Yeah.
Okay, thanks.
Sure.
Further questions?
I think there are even hardware today that has some special equipment like the Raspberry Pi, where there exists a FM radio application that makes use of a variable oscillator on the board. Of course, you should not be able to use it without a license, but these days this is really difficult to enforce. So, are you aware of other work in this area?
Specifically, talk about ways to exploit electronics to emit RF. There are some works that talk about. Specifically, with the display cable, again, I mentioned with this, we weren't the first to come up with this idea of noticing that there is RF emissions from the display cable. But in terms of using the electronics in the computer itself to emit a signal over RFs as clearly as we did with the cellular technologies, I'm not presently aware. But perhaps there are other published works on this method. But during our research, we didn't see anything in that specific category.
So, any more questions? No, then I have a question. Did you try to use any stuff that makes sound, like the fans in a system, or use the fans to manipulate the temperature?
Are you talking about as an acoustic channel?
Yeah, as acoustic channel, or maybe a thermal channel, so manipulate the fan speed so you can generate more heat?
So for the acoustic channel was not from our labs. So the only mention here that we didn't do. But in terms of fan speed for the thermal channels, yes, we did notice, of course, the fan has a great impact in terms of the exhaust brought out from the system, brought into the other machine. We didn't try playing necessarily directly with the fan speeds, though, of course, that has an impact. I think I didn't have the picture here, but when you cause a very large load on the CPU, the heat picks up very quickly. And the moment that you stop that load, it has a very steep drop in terms of environmental temperature. And the reason that's because of the way that the convection heating works. It's very efficient in getting rid of that heat when there's no need of it, or when it's in excess. So I would say that the fan speed, in terms of thermal channels, you would always want it on the highest in order to get that heat going to the other computer. And in which case, you probably wouldn't want to play around with the speed so much, as far as we've seen.
Thanks.
You could, for example, change the thermal profile from low acoustics to low temperatures, which would significantly change the behavior of the fan, or you could use printers and the noise they made.
Right. Yeah. So the idea of emitting sound, because a lot of, like, specifically laptops or smartphones come with both speakers and microphones in terms of the acoustic channels, yeah, I mean, it makes them quite easily mesh network. But once you start looking at other devices and trying to exploit the noises that they make, it's a little harder to make a deterministic channel, to deterministically make noises, but it is definitely feasible, I would say.
So thanks for the talk. I liked it a lot. I'm just wondering, because I'm not in that field, have you tried to experiment with the connected cars and the cars now? Because almost all cars will need a smartphone somehow, or at least 2, 3 in the car. And almost all will be connected to some clouds. So is there some future work or current work on that?
Well, in our research labs, we're also working on that problem. We have a wide range of different research topics that we take care of, not just air-gapping networks, also smartphone security, contextual smartphone security, continuous authentication. And one of the projects that we've taken also is smart car or connected car security. It's not a work that I'm presently involved with, but it could be some, of course, implications here in terms of bridging between those two systems.
So, do we have further questions? No? Then thank you very much for the talk. It was very interesting.